Wonderful. So let's look over what we did last time. So last time we were going back to covering spaces. So going back to how we originally computed the fundamental group of the circle. And we said that covering spaces are maps for which X has an open cover with every element of this cover evenly covered by P, right? So, i.e., open sets, open subsets, U, such P inverse of U is the disjoint union of a bunch of sets V, and P restricted to any one of these is a homeomorphism. Okay, and then we spent some time talking about how covering maps have important lifting properties. Right, so the general case corresponds to when you have some map into a space X, and then you have a you have a cover of that space X by X tilde, and you want to know when is there a lift. And what we saw is that you always have necessary that the image of the fundamental group of Y under F be inside the image of the fundamental group of X tilde with respect to P, and if Y is path connected and locally path connected, then this is also sufficient. Okay, so you want to lift a map to a cover, then the fundamental group tells you if you can do it and precisely when. Okay, we saw that lifts, if they exist, are unique. And we also saw that that covering spaces are related to cosets. In that if you have the lifting correspondence that takes a loop, lifts it up, and takes the right endpoint, then this descends to a bijection between the image group, the cosets of the fundamental group by the image group, and the inverse image of a point. So we're going to expand on the relation between covers and subgroups. So you can think of this as saying one relation between a cover and a subgroup is that if that subgroup is the image of the fundamental group, then the number of cosets is the same as the number of sheets, right? So in fact, there is a So assigning the subgroup given by the image to the cover is known as the Galois correspondence. So as you all know, Galois refers to Évariste Galois, the romantic French mathematician who died tragically in a duel at the age of 21. And of course, he's famous for, well, for dying in a duel at the age of 21, but also for his discoveries in algebra that tell you when a polynomial can be solved with radicals. As you recall from algebra, what Galois theory tells you is that let's just say it gives you a relation between field extensions and subgroups of the Galois group. So this is known as a Galois correspondence because it's very similar. We're going to have relations between subgroups of the fundamental group and covers of the space. Right? In fact, you can make this relation more than just an analogy. So if you're interested in how these things can end up being the same, you should look up Grothendieck's version of Galois theory. Okay, but in particular, what we're going to show is that for suitable spaces X, then given any given any subgroup of the fundamental group, there is a, let's say, unique, in quotes, so unique equivalence class, cover of X with H equal to the image of the fundamental group. Okay, so that's what we want to do. Given a subgroup, construct the cover, and then later talk about equivalence classes of covers and relate that to the subgroups. So if H is equal to 1, so if H is trivial, right, remember that we proved that P star is an injective map. So if the image of this subgroup is trivial, that means that this subgroup was trivial to start with. So if H is 1, then this is a cover with X tilde simply connected. And as I mentioned last time, that is known as a universal cover. Okay, so as I said, this is only going to be true for suitable X, right? So let's think about the case H equal to 1 to figure out what a suitable X should be. So what can you say about X if you know that there is a cover that is simply connected? So in that case, if so given a universal cover, if U is an open set evenly covered by P, let's say, and V is a slice above U, then any loop in U lifts to a loop in V, right, an actual loop, because P is a homeomorphism between V and U, right? So if you lift a loop that was entirely contained in U, then that lift is entirely contained in V, and it's, again, a loop. But of course, since X tilde is simply connected, this loop is null homotopic. I don't know if it's null homotopic in V or not, but it's null homotopic in X tilde. And hence, the original loop is null homotopic in X. Again, I don't know if it's null homotopic in U or not, but it's null homotopic in X. And how do we know that? Well, take the null homotopy upstairs and just project it down with P, and you will get a null homotopy downstairs. So another way of saying that is that if we include this set in X into X, so if this is the inclusion, then the image of the fundamental group is trivial. So this is equal to 1 in pi 1 of X, or 0. It's a trivial subgroup of pi 1 of X. So let's turn that into a definition. Let's say that a space X is semi-locally simply connected if each point X has a neighborhood such that the inclusion sends its fundamental group to the trivial subgroup of the fundamental group of X. Right? So again, you have a loop in U, and we're not saying that that loop is necessarily null homotopic in U, right? U might have a bunch of holes or whatever. We're saying that if you take that loop and you view it inside X, then it's null homotopic there. Okay? So, of course, this is a new word for us, semi-locally. And the thing is that if we were to say locally simply connected, this would not mean the same thing. This would mean that you have locally connected little neighborhoods, right? So that would refer to having a loop in U be null homotopic inside U. So that's why we call it something different. Not every space is semi-locally simply connected. But nice spaces are. An example of a space that is not semi-locally simply connected is a space called this, known as the Hawaiian earring. Earrings. So this looks like we're in the plane, and we have a bunch of circles, each one of which is tangent to the y-axis. So this is the union over n in the naturals of the circle of radius 1 over n and center 1 over n. Right? So it's a bunch of circles in the right half plane that all go through 0 and are tangent to the y-axis. Right? So if you look at a neighborhood, any known neighborhood of the origin has this property. Right? Because no matter how small a neighborhood you choose, there is some circle that lies entirely in that neighborhood, and going around that loop is not null homotopic in that neighborhood or in the entire space X. Okay? So this is an example of space that's not semilocally simply connected. We have many examples of spaces that are, so just think about any manifold, for example, a surface. And if you have any point, then it has a neighborhood that is homeomorphic to a neighborhood of the origin in Rn, and so it is contractible in particular, and so this property holds staying inside the neighborhood. Okay, so what we've seen is that if you have a universal cover, then it must be semilocally simply connected. Okay, so here is a very satisfying theorem. If X is path connected, locally path connected, and semilocally simply connected, then it has a universal cover. Okay, so this necessary condition is enough for spaces that are path connected and locally path connected. Okay, so we're going to prove this by directly constructing the universal cover of X. Okay, and we're going to construct it by using the fundamental groupoid, right? So notice the following. First, assume that X has a universal cover. And let X naught tilde be any point here. Then for any other point, there's a unique path homotopy class of paths from X naught tilde to X tilde. Right? So remember, if you think way back to when we first defined simply connected, we justified the name by saying that if you have a simply connected space and you pick any 2 points on that space, then a path between them, any 2 paths between them, are path homotopic to each other. Right? So That's why it's called simply connected. So there's just one choice of path homotopy classes of paths between 2 points. So the points in x tilde are in one-to-one correspondence to the path homotopy classes of paths starting at x naught tilde. Right? Of course, this because it's path connected, so you can join any 2 points by some path. But by the path lifting property, this is the same as the path homotopy classes of paths in x starting at any fixed point x naught. Right? Because if you give me a path homotopy class of paths in x tilde, I can project it down to x, and I'll get a path homotopy class of paths in x. And vice versa, if you give me a class here, I can lift it uniquely to a class up here. Right? But what's wonderful is that we ended up with a description of the points in x tilde that only used x. Right? So now, even if you don't assume that you have a universal cover, you can start with this set, the path homotopy classes of paths in x starting in x naught. Right. So let's turn this around. And define x tilde as a set to be the path homotopy classes of paths. Right? So that's an element of the fundamental groupoid of x. And we'll just demand that the left endpoint be some fixed point x naught. Right? So path homotopy classes of paths in x, and we're just demanding that the left endpoint be fixed. Okay? This has an obvious map. Where you just assign to each class the right endpoint. Right? We know that's well defined because it's a path homotopy class, so the endpoints don't change. Okay. So we have the right set. We know it's the right set because if we did have a universal covering space, then the points would be these. Would be in one-to-one correspondence with these. So we need to define a topology on x tilde that makes P continuous, first of all, and a covering map. Okay? Now, we need to define a topology. One very convenient way of defining a topology is to define a basis for the topology. So let me remind you a basis for a topology on some set Y is a collection B of subsets satisfying two properties. First, they cover Y. And secondly, if you have two elements in B, and you have any point inside the intersection, then there is another element of B that's contained in the intersection and contains the point Y. Okay, so given a basis, if you let tau be the subsets of Y that can be written as unions of sets in B, then tau is a topology on Y. So on the one hand, this is great because it gives us a way of defining a topology by a nice class of subsets. Also, it makes it easy to check if a map is continuous. So in this case, a map from Z, some space, topological space Z to Y, whose topology is given in this way, this is continuous if and only if the inverse image of a set is open for the elements of the basis. Right? So to check continuity, it's enough to check that the inverse image of an open set is open for open sets in the basis of the topology. Okay, so here's our plan. We're going to choose a basis Bx of a topology. We're going to choose a basis for the topology on X, right? So X, which is already a topological space. Then what's going to be special about these is that for each, say, U alpha in this basis, we'll decompose the inverse image under P as a collection of subsets of X tilde, right, indexed by some index beta, with P restricted to any one of these, a bijection, and then we'll show that Bx tilde consisting of all of these putative slices is a basis for a topology on X tilde. Okay? If we can do that, it'll follow easily that P is a covering map and continuous. And then we'll worry about X tilde being simply connected. Okay, so that's our plan. We need to choose a basis so that P behaves as if it were a covering map, and then that'll give us a basis for X tilde that actually makes it a covering map. Okay. Okay, and how we're going to choose this basis for X should be pretty clear from the hypotheses we assumed. Right? So we assumed that X was path-connected, locally path-connected, and semi-locally simply connected. So let's let Bx be all of the subsets of X such that U is path-connected and the inclusion sends the fundamental group of U into the trivial subgroup of the fundamental group of X. Okay, so our hypotheses guarantee that X is the union of all of these U's. Right? Because we know that every point in X has a neighborhood that is path connected and that has this property for the fundamental group. Okay, we want this to be a basis. We have the first property, we need the second one. Okay, but locally path connected. Excuse me. So if U1 and U2 are sets like these, and Y is in the intersection, well, since this is an open set, the locally path-connected property tells us that there is some open subset of X that contains Y and that is contained inside this intersection, and is path-connected. So then there is an open set inside this containing Y that is path connected. Okay, so great. That's almost enough to be in here. We still need to check this property. Moreover, if you have this and you want to include it inside X, well, that factors through the inclusion of any one of these sets. Right, so if I have a point in here and I want to include it in X, I can include it in U1 and then include it in X, and I get the same thing. So since this diagram commutes, then the corresponding diagram of fundamental groups commutes. So that tells us that the image of this fundamental group inside here, along the inclusion, is contained in the image of the fundamental group of U1 inside here along its inclusion, right? But the image of this group in here is trivial. So the image along its inclusion of the fundamental group of V is trivial inside the fundamental group of X. Right? So those two properties together tell us that V is in Bx, and so Bx is a basis for the topology on X. Right? So that's the first step. We found a basis. Now to make sure that this basis is good for us, we need to check that the inverse image of one of these sets breaks up into these slices for P. So given call it U alpha inside Bx, well, by definition, the inverse image of U alpha is the disjoint union over points in U alpha of homotopy classes of paths in the fundamental groupoid of X with the property that the left endpoint is X naught and the right endpoint is X. So, okay, that's what we get as a set, the big set. We want to break it up into subsets, right, with the property that when you restrict any one of these subsets, you get a bijection, right? So what we're going to do is define an equivalence relation here and look at the equivalence classes under this relation as these slices. So let's say that two elements of this inverse image are equivalent in U alpha, or with respect to U alpha, if there is a path contained entirely in U alpha such that the composition, the concatenation of a representative here with G gives you a representative here, right? So two classes are going to be equivalent in U alpha if there's a path that's contained entirely in U alpha that'll take you from a representative in one class to a representative of the other. Right? Of course, I could take the opposite path, so this is a symmetric relationship. So I'll let you check that this is in fact an equivalence relation, and we'll write P inverse of U alpha equal to the composition V alpha beta for the decomposition into equivalence classes. Equivalence classes with respect to this relation. Right, so to be more specific, to be more explicit about these guys, we can say that if you have any path in one of these, then you can write this equivalence class as the path homotopy classes f dot g, homotopy groupoid, in the fundamental groupoid of X, such that G is a path in U alpha with G of 0 equal to F of 1. Right? So as soon as you fix one path that goes from X naught and lands you inside U alpha, then the equivalence class is just all of the paths into points in U alpha that go from X naught into U alpha along the path you started with, right? So different equivalence classes correspond to different ways of going from X naught into U alpha. Once you get into U alpha, then the elements of an equivalence class are just going from the point in U alpha to another point in U alpha while staying in U alpha. Okay, so because of that, it's easy to see that P from any one of these equivalence classes to U alpha is bijective. All right? Because surjectivity is just because U alpha is path connected. While for injectivity, it's because if you take the inclusion of U and you map in the fundamental group of U, then this is trivial in the fundamental group of X. That is to say, loops in U are contractible in X. Okay? So the key fact here is to remember that these homotopy classes, path homotopy classes, are in X, right? So I'm allowed to do any homotopy I like anywhere in X, right? So if I have, to show that it's injective, assume that you have two elements here that map to the same point in U alpha, right? So this map is just looking at the right endpoint. So if you have two elements in here that go to the same endpoint in U alpha, that means that I have, if I do one and then go back along the other, what I have is my path F that gets me into U alpha, and then all I'm doing is putting a loop at the end, but that loop stays entirely in U alpha. So this loop is, it's not contracted, null homotopic. This loop that I have here at the end is null homotopic inside X. So I might not be able to homotope it away staying inside U alpha, but I don't care. I can homotope it away inside X, and this is a path homotopy class inside X. So I can just remove that, and that's why it's injective. Okay. So wonderful. We've got a basis for the topology on X, and it does have this property that it breaks up the preimage of P into slices that then P puts in bijection with U alpha. So what we need to show is that if you just take these slices as subsets of X tilde, you get a basis for a topology, and then that topology will make P a covering map. Okay, so let B X tilde be all of the V alpha beta defined in this way. Okay, so we want to show this is the basis of a topology on X tilde. So the first part is easy. So clearly X tilde is equal to the union of B alpha beta, or you take the union over alpha and beta. And that's because the U alphas cover X. And if you take all of the V alpha beta for a given alpha, you get the preimage of U alpha. So this covers all of the preimages of all of the U alphas, so it covers all of X tilde. On the other hand, if Y in X tilde is in the intersection of two of these sets, then first find U in the basis of X such that P of Y is contained in U, which is contained in U alpha intersect U beta, alpha prime, right? But where, of course, U alpha is the projection down of B alpha beta, and U alpha prime is the image of B alpha prime beta prime. Right, so because we know that we have a basis for x, we can find a basis element that sits inside the intersection of these two elements. So then let V in the inverse image of this basis element be the equivalence class containing Y then, since equivalence in U implies equivalence in U alpha and equivalence in U alpha prime, then we have that V sits inside V alpha beta intersect V alpha prime beta prime as required. So this is a basis. And with this topology, this is a covering map. Okay? Right, and so why is this true? Well, remember, equivalence in U just means that you can, the two paths that you're looking at differ by a path that stays entirely in U. Right? But if you have a path that stays entirely in U, then you also have a path that stays entirely in U alpha and a path that stays entirely in U alpha prime. And so that's why being equivalent with respect to this implies being equivalent with respect to both of these. Okay, so we get a topology and we have a covering map. So wonderful, all that's left is to check that this total space is simply connected. Okay, so given our base point in X, let let's call it X naught tilde be the lift of the constant loop in X tilde, right? So X tilde consists of path homotopy classes of paths starting at X naught. So the constant path starting at X naught is such a thing, and so it has an equivalence class, and we'll just let that be the base point upstairs. So let's look at how it looks to lift a path from X to a path on X tilde, right? We know it's a cover, so we know that it is possible to lift a path, and in fact, there's a unique lift of a path as soon as you fix the base points. So here's a base point, and here's a point sitting above it in X tilde. So let's look at what the lift of a path starting at X naught looks like starting at X naught tilde. So given a point in x tilde. So remember, f is a path in x starting at x naught, and this is its path homotopy class. So let f sub t be the path obtained by restricting f to the interval 0 t. Right? So f1 would be f, and f0 would be the constant loop at x naught. So then t maps to the path homotopy class of ft is a path in x tilde going from the class of f0, which is x naught tilde, to the class of f1, which is the class of f, such that p of ft is equal to ft at 1, which is just f of t. So this is the lift of the path f. So the lift of f is f tilde 0, 1, x tilde, t goes to the path homotopy class ft. Okay, so that's how you lift the path. Now we know that the image under a covering map consists of the classes of loops that lift loops at x naught in x. That lifts to loops at x naught tilde in x tilde. Okay, so let's say that you have such a thing. Let's let f be in this image. Right? That means when I lift it to a path, so when I do this, then I end at x naught tilde. Right? This implies that f tilde of 1 is equal to x naught tilde. But f tilde of 1, according to this, is precisely the class of f. And x naught tilde is the class of the constant loop. So we see that if you're in the image, then you are path homotopy equivalent to the constant loop. And that's exactly what it means to be the 0 element. All right, so this shows that this is 0 in pi 1 of x naught. But since we know that the induced map from a covering map is injective, if the image is just a trivial element, then this group has to have been the trivial element. Right? No, let's say 0. It's a trivial group. Thus, x tilde is simply connected, and that shows that it is the universal cover. Right? So that shows that if you have a space that is path connected, locally path connected, and then has this new property, semi-locally simply connected, then just looking at path homotopy classes of paths in X that start at a given point, that gives you a space x tilde that has a natural topology that makes the endpoint map a covering map from a simply connected space. So you have a universal cover. Okay. Okay, but we started out by saying that we were interested in showing that every subset, every subgroup of the fundamental group corresponds to a cover for reasonable x. So just looking at the subgroup equal to the identity, just the trivial subgroup, we found conditions that make x reasonable, and we proved that you have such a thing. So it turns out that once you have this, the general case follows. So corollary, if x is path connected, locally path connected, and semi-locally simply connected, then for every subgroup of the fundamental group, there is a cover, let's call it x tilde h to x with p sub h, and a point x naught tilde in x tilde h, such that the image of pi 1 of x tilde h with this base point is equal to h. Okay, so notice the statement says that there is a covering space and a point, right? So you'll recall that if you change base points, then we have an isomorphism between the fundamental groups, and that isomorphism is given by conjugating by the homotopy class of a path joining the two base points. So of course, the base points we're interested in all lie in the same fiber above a base point for x. So that path joining them descends to a loop. So it turns out that if you were to pick another base point, then you're not guaranteed to get this subgroup H. You might get a subgroup conjugate to it within the fundamental group of X. Of course, if H is normal, then that subgroup is again H. But if H is not normal, then you might get something else. Right? But what this says is that if you pick the base point appropriately, then you will get H. For normal subgroups, again, the choice is irrelevant. Okay, so proof. So let x tilde be the universal cover that we just constructed. And let's define an equivalence relation with respect to H So this is for 2 points in X tilde. If so f of 1 is equal to f prime of 1, and the loop that you get. So remember, points in X tilde are path homotopy classes of paths in X that all begin at the same point, X naught. So here we're asking that they have the same right endpoint. And so that lets you concatenate one with the inverse path of the other one. And so that's going to give you a loop at X naught. And we're demanding that that loop be inside H, which is a subgroup of pi 1 of X, X naught. Okay? So if that happens, we'll say that these are equivalent. Right? Now, this is an equivalence relation precisely because H is a subgroup. Right? So a loop, a point is equivalent to itself because you have the identity. If you have f equivalent to f prime, then f prime is equivalent to f because given an element in H, you have the inverse. And because you can multiply in H, you have transitivity. So this is an equivalence relation, and we define X tilde H to be the equivalence classes. X tilde mod out by the H equivalence. Notice that the map P that we defined on the universal cover, remember that just takes the right endpoint of a curve. And any two equivalence classes that we're identifying with this relation have the same right endpoint. So the map P descends. Right. Which is to say that we have X tilde, and you can map down to X tilde H just by taking the equivalence class with respect to this relation, and you can map down to X, and this is a commutative diagram. Okay, so in particular, it descends to here, and it's still a covering map with the topology induced on this from X tilde. So if we use as base point the one we used last time, so take this X tilde, well, what did I denote it? Just X tilde. As base point, this, the equivalence class of the constant loop at X naught, then the image of the lift of a loop is a loop precisely when its homotopy equivalence class is equal to the equivalence class here. But the equivalence class of this constant is precisely H. So that shows that we have a cover for H so that the image of the fundamental group is exactly H. Okay, so let's do an application. So here's an application to algebra. Let's go back to the example we had last time of cover of the bouquet of two circles. Right? So when we were looking at that, I pointed out that because we had a graph, the covering space had to be a graph itself. So let's use that to prove something in algebra. So just note that the fundamental group of a graph is always a free group. Okay, so let's think about this through an example. So let's say that your graph consists of the one skeleton of a cube. All right, so what you can do is pick a maximal tree. Pick a spanning tree. All right, so so in this case, for example, we could do this. So a spanning tree, so a tree is a graph where two vertices are connected by a single path. Right, so if you want to go from one vertex to another, there's only one way of doing that. There are no loops or anything, no circuits. And then spanning, what I mean is a tree that contains all of the vertices. So it's a fact that every connected graph has a spanning tree. If you have a finite graph, that's easy. Just pick a vertex and then pick any edge. Pick a vertex, and then inductively, if you've constructed a tree, then either it has all of the vertices or it doesn't. So if it doesn't, then pick a vertex that you can join by adding an edge and add it. Since that vertex wasn't connected before, then you still have only one path joining any two vertices. And then you can just iterate until you've gotten all of the vertices. If you have an infinite graph, then you have to use Sorn's lemma. You have to use some version of the axiom of choice to prove that there is a spanning tree, but you can. So once you have a spanning tree, let's call that T. Let E alpha be the edges not in the spanning tree. For each E alpha, let U alpha be an open set obtained from T union E alpha by just thickening it up. Thickening up a little. Right? So just thicken it up a little. You don't want to include any other edges except the ones that are in T union E alpha. Right? So then you're guaranteed that this open set has this subset as a deformation retract. Right? Then apply Van Kampen. So applying Van Kampen, we see that the fundamental group of the graph is equal to the free group of one copy of z for each e alpha, for each edge not in the spanning tree. Right? So if you think at this graph, then we're using as spanning tree these edges right? So if you like, this is a contractible set. This contracts down to a point. And if you were to do that contraction, you would end up with a bouquet of loops, and you'd have one loop for every edge that's not in your spanning tree. So the fundamental group is then just the free product of copies of C, one per each alpha. So another way of saying that is that you have the free group with one generator per each E alpha. Okay, so the fundamental group of a graph is always a free group. So then our application is that every subgroup of a free group is a free group. Okay, this has a name. This is known as the Nielsen-Schreier theorem. It was proven in 1921 by Nielsen, and then 1926 by Schreier. Nielsen did it for finite free groups with finitely many generators, and Schreier did it in general. So this is true regardless of how many generators you have. Okay, the topological proof is a little bit later, from 1937 or so. It was done by Reinhold Bayer and Friedrich Lebbe. Bayer, incidentally, was a professor here at UIUC. And the proof is very quick, given what we've done. So if you have a free group, so that's the fundamental group of a graph, the every subgroup corresponds to a cover. That cover is again a graph, and so its fundamental group is a free group. And since that was an arbitrary subgroup, you're done. Right? So just note that every subgroup is the fundamental group. No, it's isomorphic to the fundamental group of a cover. And every cover is, again, a graph. So let's look at an example. So let's say that we have the bouquet on two circles here. And let's look at a cover with two sheets. So for A, we're just going to take two copies. And for B, we're going to have one going up and one going down. Right? So again, the labels that I'm putting up here correspond to what they project down to. These are, of course, different paths. These are different paths, for example, upstairs, and these loops are not being identified. Right? So right, we could call this x and x tilde. So we know that the fundamental group of x is the free group on two generators, A and B. Upstairs, x tilde is a graph. And so we look at a spanning tree. So for example, there's a spanning tree. Right? It connects all of the vertices. And And so you get one generator for everybody not on the spanning tree. So you have 3 generators, right? So pi1 of x tilde is the free group on 3 generators. Let's just say free on 3 generators. And the image of pi1 of x tilde is the free group on, and we can see what the generators are. So if we pick this as our base point, then let's see, we have this loop, and that gets sent down to A. Then I can go down along B and back along B, so I have B squared. Or I could go down along B, then do A, and then go up along B. So I have B, A, B, B, A, B. So those are what the generators map to in pi1 of x. And because it's injective, we know that this is, there are no relations between these generators in here, because it has to be the free group on these generators. So that shows that the free group on 3 generators is a subgroup on the free group on 2 generators, which is sort of remarkable. And we will stop there and pick it up on Tuesday.